It should be a pretty quick one here. We'll slow it down in part B and we'll make sure we talk about that. But they give us a cylinder, they give us the DHDT, how fast that height's changing. And you know, this is already shaping up to be a related rate problem. They even hook us up with the volume formula, right? So I start with that volume formula. Part A says find the rate of change of the volume. So we know that means we're going to find the dVdt when the height of that water is 4 feet. So when that H is equal to 4. The nice thing is, since they gave us a cylinder, the radius is always equal to 1. It's not changing like on a cone. So the radius is always equal to 1, which means you can use that number always. It's not a variable, so you can just plug that 1 in right away. So here's your volume equation that you're starting with, and then just take the derivative with respect to time. So the derivative of V is dV dt. Now this is just like 5 times x. Like the derivative of 5x is like 5, right? The derivative of 5h is 5, so the derivative of pi h is just pi. But if you take the derivative of x's with respect to time, you got to tag on the dx dt, the dr dt, the dy dt. So I did the derivative of h's with respect to time, got to tag on that dh dt right there. And then they said when h is equal to 4. So when I went to plug the 4 in, I was like, oh, there's no h. So I got to plug in what the dh dt is equal to. So I plugged that in for the dh dt. Then I took the 4, plugged in there for the h. I got that negative pi over 5. Now, be careful. It does say indicate units of measure. You know how to do this. It says how fast the volume is changing. So the volume unit is always cubic units, and it's how fast it's changing. So it should be that rate, cubic feet per second there. Now, letter B says when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? Explain your reasoning. Now, I know when you see increasing, decreasing, you're thinking that first derivative right there, right? But be really careful here. It doesn't say is the height increasing or decreasing for you to look at is dHdt positive or negative. You're not looking at that first derivative. It says when is the rate of change of the height increasing or decreasing? Now the height is h. The rate of change of the height is the derivative. The rate of change is your derivative. That is your dHdt. They want to know where that is increasing or decreasing. So you got to look at the second derivative and figure out where that's positive or negative, right? So it doesn't matter what the graph is. If I say this is the graph of like the 37th derivative, and I say, where is that graph increasing? If this is the 37th derivative graph, and I say, where is that graph increasing? You're looking at where its slopes are positive. Well, if you're looking at where the slopes are positive, you're looking at where its derivative is positive. So you're looking at, hey, where is that 38th derivative graph positive? If I say, where is this decreasing? That's where that 38th derivative graph would be negative. So anytime you want to figure out whether anytime you want to maximize or minimize something, you take its derivative, you figure out where it's equal to 0. Anytime you want to figure out whether something is increasing or decreasing, you take its derivative and figure out whether it's positive or negative right there. So we also had that same concept back in number 1 on this same packet right there. So again, height is the h, rate of change is the dHdt, and they're asking is that derivative increasing or decreasing? So take its derivative, which is the second derivative, and determine whether that's positive or negative. So I started with the first derivative, and I took the derivative there. There's your notation for that. And then I just multiply by the power, decrease the power by 1. Remember to tag on the dHdt right there. And then I got rid of the negative exponent. And then when I substituted again for the dHdt, I plugged the formula in for the dHdt. Turns out on this one, I was getting ready to take this 3 and plug it in for the h's, but it turns out that the h is completely canceled out. I got a negative times a negative, which is a positive 1 over 200 right there. So they could easily give us something where you actually plug in the 3 for the h and get a number for that. But this is saying that the derivative is always 1 over 200. So that means the second derivative is always 1 over 200. So if that second derivative is that means it's always a positive number, which means like the original curve is like concave up, right? But we don't care about that. But like, so if you want to figure out whether something is increasing or decreasing or not, if its derivative is positive, it's increasing. If its derivative is negative, then it's decreasing. So since that second derivative is positive, that's the derivative of that first derivative. So that first derivative is positive, which means that first derivative graph is going to be increasing. So I just put increasing since that second derivative is positive right there. So kind of a little tricky wrench to try to throw at us, but it was like a number of 1 and 4, so it's good we're getting exposed to that. And in letter C, we should be perfectly strong with these by now. It tells us to find h. You're given dHdt, separation of variables. You go from your derivative to the original function, you know that's going to be integrating both sides. So separate your variables, integrate both sides, remember your plus c, use the point that they give you to plug it in to figure out what that c value is, and then solve that for the y or the h in this case. So I started with the derivative, move the dt over, and then you got to get the h's with the dh. So I divided both sides by the square root of h. I knew 1 over square root of h was just h to the negative 1/2, and then leave the extra stuff or any t's with the dt integrate both sides. Easy integrate. That's h to the 1/2 divided by 1/2, which means you're going to times it by 2. Tag on the t there, integrate it. Got your plus c right away, and then plug in the point. If you ever get stuck with which is x, which is y, remember it's usually dy over dx, right? And so when they switch to dh over dt, that means that's like your y variable. That t is like your x variable. So when it said t equals 0, that's my x. When it says that height was 5, there's a y. So plug the 5 in for the h, 0 in for the t, you get your c value, plug that back in, and then you just solve that for the h because it says find an expression for h in terms of t. So just solve that for h. I just divided everything by 2, squared both sides, done. But that should be a strength of ours already here. Orbit. I like that word, orbit. I wonder if I could still become an astronaut. I think that'd be pretty cool to kind of float around in space there a little bit. But yeah, orbit.